We'll finish off our study of the solar system by looking at the outermost reaches of it, the Kuiper Belt and the Oort Cloud, the proposed sources for short period comets and long period comets. First, why do we need a source for short period comets? Comets are temporary objects. With every close approach to the sun, every time they visit the inner solar system, a significant chunk of their material evaporates away. Consider Comet Halley with a period of 76 years. In only 7,600 years, it will complete 100 orbits, with each orbit losing some of its volatile material. The volatile material is the stuff that vaporizes and is blown away as it nears the sun. So what percent does it lose each orbit? We don't know, but they can't last forever. They keep losing stuff. Eventually, there will be nothing left but the rocks that make up the core of the comet. So what is the Kuiper Belt? A donut-shaped region beyond Neptune's orbit, and it would be part of a larger group of objects called trans-Neptunian objects, although that's something we've come to learn by studying the things out there. It ranges from about 30 to 50 astronomical units from the sun, so a fairly large range, much larger than the asteroid belt. Here's a figure from the NASA site of the Kuiper Belt. The actual Kuiper Belt won't have that stamped on it up there saying Kuiper Belt. The figure makes it look more like a disk than a donut. Imagine that it extends a bit more above and below the plane of the planetary orbits. Maybe up as far as Pluto and down as far as Pluto is above it. Now, the first Kuiper Belt object discovered was Pluto, and the one discovered in 1992 was actually the second. This is the two pictures that were used to detect the 1992 object, which got the name of 1992 QB1, and you can see in the circles on there how it had moved from one of the pictures to the other. I don't have the date for the second picture down here, so I don't know when it was taken or how long it took to move that far. But the same sort of technique was used that Clyde Tombaugh used, some sort of a blink comparator. Nowadays there's computer software that will do some of the searching for you, comparing the images and looking for things that change. But whatever it flags as motion has to be checked by a human, because there are a lot of false positives in the searches. Since 1992, a few more objects, and I put the word few in quotation marks because, well, look at the next slide. Far more than 2,000 Kuiper Belt objects have been discovered so far. Astronomers estimate there are hundreds of thousands of objects, at least 100 kilometers wide or larger. Here we're looking at the solar system from the orbit of Jupiter on out past Neptune's orbit. So there's Jupiter's orbit, the innermost circle on there, and then Neptune's orbit is the outermost planetary orbit drawn on there. See all those white dots? Those are objects like Pluto. They complete 2 orbits for every 3 that Neptune completes, or in one of their orbits, Neptune will complete 1.5 orbits. Pluto just happens to be the largest of those objects, as far as we know now, and thus it was the easiest one to find, and it was probably the only one that could have been found with the 13-inch telescope that Clyde Tombaugh was using. Pluto is just one of many objects with that resonance, and one of many thousands of Kuiper Belt objects. So if you want to call Pluto anything, call it a Kuiper Belt object that just happens to be large enough to also be called a dwarf planet. And that's a nice, accurate description for Pluto. More about the Kuiper Belt. It's similar to the asteroid belt, but far larger, 20 times as wide and 20 to 200 times as massive. And the asteroid belt tends to be pretty flat. Nearly all the asteroids are pretty much in the plane of the planetary orbits. The Kuiper Belt has that vertical dimension to it that makes it more of a donut than a disk. Now, in the Kuiper Belt, the objects are mostly made of ice of various types, whereas in the asteroid belt things are rocky or metallic. In the Kuiper Belt, the classic Kuiper Belt objects have stable orbits, and they're probably not the source of the short period comets. We'll look at something for those here in a little bit. In fact, we'll look at them right now. Other trans-Neptunian objects, the scattered disk. Trans-Neptunian just means beyond Neptune. These objects are thought to have been tossed out, farther out, from gravitational interactions with the gas giants. That disruptive effect that Jupiter has on comets, the other gas giants can have that on things as well, and so they can be flung out of the inner part of the solar system or closer in and tossed farther out. The scattered disk objects are similar in makeup to the Kuiper Belt objects, so mostly ices, some rock. The orbits are more elliptical. Near points 30 to 35 astronomical units, which is 30 astronomical units is Neptune's orbit. So they get in about as close as Neptune, but their far points can be well beyond 100 astronomical units. And so that's beyond the Kuiper Belt. Now, we know that these things exist because we've studied the orbits of the things that have been detected in the Kuiper Belt, and they split into two categories where we have these scattered disk objects. Scattered disk does overlap with the Kuiper Belt, and so we see these. And these are most likely the source of short period comets. Let's take a look at that plot again. All the red objects are classic Kuiper Belt objects on stable orbits. The magenta objects are scattered disk objects on orbits that may have them passing through the Kuiper Belt at times, but they'll range far outside the belt and a ways inside it as well. I hope it's obvious that the existence of the Kuiper Belt is a confirmed hypothesis and that we've found a likely source of short period comets. Before we look at possibilities for long period comets, let's have a look at one particular Kuiper Belt object. This is Asteroid. It was named that after the New Horizons spacecraft flew past it. After it had gone by Pluto, they started looking for possible Kuiper Belt objects that it might visit without having to expend too much fuel, and so it took a look at this. This is an unusual object. Semi-major axis, 44.6 astronomical units, so it's on average a little more distance than Pluto is. Takes a little bit longer to orbit. Dimensions are just plain weird. The 36 kilometers is from the far left end to the far right end. I didn't get the ingredients for it, but I did read that there were ices on the surface of it. Needless to say, this is a very unusual shape. The two parts of it probably started as separate objects and then were attracted to each other through their mutual gravitational attraction, and they're not terribly massive objects, so that gravitational attraction wouldn't have pulled them toward each other very rapidly. When they did collide, whatever collision occurred was gentle enough that it didn't knock the two things into pieces. They just kind of stuck together. And so that's what we see here. Right now, the New Horizons mission is looking for additional Kuiper Belt objects that it might fly by without expending all the rest of its fuel before its instruments die. The instruments are expected to survive until about 2030. So let's look at this proposed source of long period comets, the Oort Cloud. It's a spherical region this time, not a donut. This is something that surrounds the entire solar system in every direction, and it ranges from about 10,000 to 100,000 astronomical units from the sun. And so there would be some big gap between the outer edge of the Kuiper Belt and even the scattered disk objects before you get to this Oort Cloud. And by the way, that 100,000 astronomical units, 1.6 light years, that reaches a third of the way to the next nearest star right now. And if it has its own Oort Cloud, that might reach just as far. Those Oort clouds aren't going to be all that far away from each other. The stars in the Milky Way galaxy are in motion around the center of it. The sun is one of those stars. The nearby stars have times or distances to them that vary in time, and there may be stars that come within 2 light years of us at some point. If that's the case, that star, that other star, would exert a greater gravitational force on the outer edge of our Oort cloud than the sun does. And so you can have Oort cloud objects exchanged, perhaps, or flung into the inner solar system in some kind of an interaction. So that's what is expected to send objects from the outer region, from the Oort cloud, in toward the inner solar system. However, so far, the Oort cloud is just a hypothesis. We see some objects coming in from that far out in space, and we see comets that have really long periods, but we don't know for sure that they came from a place like the Oort cloud. That's just a hypothesis so far. And anything that's out there is too distant to be seen with today's telescope. If you think about it, if it's 10,000 astronomical units out there, the intensity of sunlight that falls on it is going to be the square of 10,000, 1 divided by that. Square 10,000 and you get 100 million. Okay, the light that falls on an object out there will be 1/100 millionth of what falls on the Earth. And it's not going to light it up very much. And then for us to see it, the light that falls on it is going to have to reflect back toward us, getting dimmer all the way by a factor of a whole bunch. And so we're going to have much different telescopes to be able to see things out there. The James Webb Space Telescope isn't large enough to do it. For more information about the Kuiper Belt, the scattered disk, and the Oort cloud, see the Wikipedia articles on those things. They're quite interesting with a lot more information than we have time to look at. Well, that ends our study of the solar system.